Hello everyone. Today's topic is CPU scheduling. Objective of this chapter is to introduce CPU scheduling, which is the basis for multi-programming operating system, and to describe various CPU scheduling algorithms, to discuss evaluation criteria for CPU scheduling algorithms, and to examine the scheduling algorithm of several operating systems. Scheduling criteria, we have some features like CPU utilization. CPU utilization means keep the CPU as busy as possible. Second is throughput. It means number of processes that complete their execution per unit time. Third is turnaround time, amount of time to execute a particular process. Waiting time, amount of time a process has been waiting in the ready queue. Last one is response time. It is amount of time it takes from when a request submitted and until the first response is produced. It's not the output, it's just the first response we get from the request. That is response time. So, algorithm optimization criteria is to maximize CPU utilization, maximize throughput, minimum turnaround time, minimum waiting time, and minimum response time. First algorithm is first come first serve algorithm. In short, it is FCFS, first come first serve. Here is an example. We have three processes P1, P2, P3. Their burst time is 24, 3 and 3. Suppose the processes arrives in order P1, P2 and P3 and we will make a chart of this. So first P1 comes, its burst time is 24, so 0 to 24 is given to process P1. Then P2 comes, so time 24 to 27 given to P2 and then 27 to 30 given to P3. So if we will calculate waiting time for P1, it is 0 because P1 just came and CPU is allocated to this process. For P2, it is 24 because P2 have to wait for 24 milliseconds. Then P3, waiting time for P3 is 27. So we will calculate average waiting time 0 plus 24 plus 27 and divide by 3. We will get 17. So if we will solve this numerical using first come first serve, we will get average waiting time of 17 milliseconds. Next is shortest job first scheduling. In this algorithm, associate with each process the length of its next CPU burst. We will associate the length of next CPU burst to every process. Okay, using these length, we will schedule the process with the shortest time. If we will compare previous algorithm or uh, the other ones, then we will get the optimal average waiting time in shortest job first. But it has some difficulty that we have to know the length of the next CPU burst. Answer is that we could ask the user about it. Example is we have process P1, P2, P3, P4 and their burst time is 6, 8, 7 and 3. We will make its chart. So 0 to 3 will given to P4 as the shortest job first. So P4 has the minimum burst time. We will put it first or we will allocate the CPU first to P4. So 0 to 3 will be given to P4. Then next shortest job is P1 with burst time 6. So P1 will allocate it to the CPU. Then P3 and then P2. So next we will calculate average waiting time. P1 for P1 it's 3 because P1 have to wait to time 3. For P2 it is 16, for P3 it is 9 and for P4 it is 0. So average we will calculate, we will add this 4 waiting times and divide it by 4, we will get 7. So shortest job first, the average waiting time is 7. Next algorithm is shortest remaining time first. If we add the concept of varying arrival times and preemption to shortest job first, we will make shortest remaining time first algorithm. Uh, we will explain it or we will understand it using an example. We have process P1, P2, P3, P4. Their arrival time is 0, 1, 2, 3. Bus time is 8, 4, 9, and 5. And we will make chart for primitive shortest job first. Process P1 arrives at time 0. So we will allocate the CPU to process P1. At 0 to 1. At time 1, P2 arrives. We will compare the remaining bus time of the processes. P1 has remaining time 7 and P2 has remaining time 4. So the minimum is P2. So we will allocate CPU to P2. Then at P3, then at time 2 P3 arrives. P2 has bus time 9, P3 has burst time 9 and P2 has remaining time 3. So minimum is 3, P2 will continue. Then P4 arrives at time 3, its burst time is 5, P3 has 9 and P2 has 2. So minimum is 2, so P2 continues till 5. Okay, then P4. P4 because it has minimum burst time now. Then P1 and then P3 in this way. If we will calculate the average waiting time for P1 it is 10 minus 1 because P1 uh, for P2 it is 1 minus 1 because P2 just arrive at time 1 and will get a CPU at time 1 so it has 0 waiting time. Then we will calculate for P3 it is 17 minus 2 and then for P4 it is 5 minus 3 and we will divide it by 4 and we will get the average waiting time 6.5 milliseconds. Then it is priority scheduling. In this algorithm, a priority number, it is an integer number, a priority number is associated with each process. The CPU is allocated to the process with the highest priority. And smallest integer means highest priority. It means if we have integer 1 and we have integer 2, so the highest priority is for integer 1. It may be primitive, it may be non-primitive. It has a problem of starvation. It means a lower priority process may never execute. For example, a low priority is waiting for the CPU. A process comes with a high priority, so the CPU will allocate it to higher priority, then next come with higher priority with higher priority. So it may happen that never lower priority process will never execute. To overcome this, there is a solution of which we call aging. Aging means as time progresses, increase the priority of the process. Okay, so that the lower priority at some time will become a higher priority and it will execute. For example, we have process P2, P1 to P5, but time is given, their priority is given. As we can see, P2 has the highest priority, then we have P5, then we have P1, then we have P3, and then we have P4. We will make chart of these processes on base of their priority and we will calculate the average waiting time. If we will calculate the average waiting time like previous algorithms, we will get 8.2 milliseconds for this numerical. Next is round robin. A difference between previous and this algorithm is that each process gets a small unit of CPU time. Okay, a fixed unit of CPU time. Uh, we will say it a time quantum and represented by small q. It is usually 10 to 100 milliseconds and after that time elapsed, the process is preempted and added to the end of the ready queue. It means a process will get the CPU for this time period only, for this time quantum only, and when the time quantum expires, it will it will be deallocated the CPU, and the next process will uh, execute in the CPU. Okay, there is a time interrupter every quantum interrupts. There is a timer that will interrupt every quantum to schedule next process. For example, process P1, P2 and P3 burst time is 24, 3 and 3. If on basis of round robin, we will make a chart 0 to 4 will given to P1, then we have 4 to 7. Uh, Quantum is of 4 to 8, but burst time of P2 is just 3. So 4 to 7 is P2, then 7 to 10 is P3. P2 and P3 have 3 and 3 burst time, quantum is 4. So they will execute or they will terminate before the time quantum expires. Okay, then next time quantum is 10 to 14 for P1, for 14 to 18 to P1, P1, P1 as 24 burst time for P1. If you will calculate the average waiting time for P1, P2, P3, it will be 5.66 milliseconds. Typically, this algorithm have higher average turnaround time than shortest job first, but better response. And Q should be large compared to context switch time. Q must be a large, not very small. Q usually 10 milliseconds to 100 milliseconds, and context switch less than 10 seconds. Okay. Thank you so much.